just a piece of information. I have many questions coming along the way, and if I get correct questions from any of you, I'm going to give a special reward. I'm not bluffing, I'm really serious. Okay, so the first question, even before I get into all these formula and stuff, why do we exactly use precision and why do we exactly use recall? So short answer is accuracy doesn't work anywhere. So accuracy works in some problems, but for all the questions we certainly can't use accuracy. Let me give you a few examples. Okay, imagine someone has claimed to create a model to identify particular terrorists who are going to board flights, and he or she claims that the model has an accuracy of around 99 to 99.5%. So would you believe them? So we pay 7 to 7.5k for each flight, I guess. And if some guy in the airport comes and tells you, there's a 99% chance that there's a terrorist on the flight, would you go or would you not go? So I would certainly go because I know data science. I know this is not true. Yeah, this is the question. And let's dig deeper into how this particular person would have built a model. So let's label every single person from, let's say, US airport or Indian airport as not a terrorist. So all of us, we know that we are not terrorists. So let's label all of us as non-terrorists. And given that there are around 800 to 900 million passengers traveling on US flights per year, and there are only 17 come from terrorists, and this is the data from 2000 to 2017. So this model, as you can see, with basic math and the accuracy formula that Ayush has given, would yield accuracy of around 99.99%. And let's say, another example in the financial domain. So ICICI Bank wants to build an ML model to predict if customers would default a loan or not. They hire a team of amateur data scientists who work on this problem, let's say a few interns. And the data scientists, they go on Kaggle to collect data sets. So I'll also explain why Kaggle is not the right place to find data sets. And one person finds a data set with a certain number of features and labels whether a client defaults a loan or he doesn't default. So there are 1 million data points, and obviously of Indian customers in the data set. And everyone on the team is satisfied with the data set that's collected. They go have lunch and all, and they have a party. But do you sense a problem? So I certainly sense a problem here. Out of all the 1 million data points, let's say only 200 are labeled as loan defaults, and all the others are no loan defaults. Okay, so these 200 maybe people like Vijay Mallya and Nirav Modi who are like thousands of crores of loans, and it could be me or you who has just thousands or lakhs of loans that are defaulted with ICICI Bank. So how would I build this model with this data? So let me just build a dummy model with some logistic regression that always predicts that the loan defaults in every single case. So if we have 1 million data points, I feed some test data, and always it's predicted that the person defaults the loan. Then what would be the accuracy? So here the performance metrics would be, I take it as accuracy. It would be around 99%, right? So that's really good. But we know that this is not going to work in production, and the reason is that once ICICI starts deploying this model everywhere, they happily give out loans to everyone saying that we have so and so model and everyone's going to default, we are going to extract money from them. But eventually what happens is the bank runs out of money, they give loans to everyone, and eventually it shuts down. So that's what's going to happen. So there are other hundreds of applications where accuracy literally fades. So in medical domain, like as we have been working on special topic projects, so you can't use accuracy to predict whether a person has cancer or not. In the tech domain, you can't predict whether an email is spam or not, just given the accuracy. And weather detection, this is really interesting, is ISRO can't decide when to launch a satellite based on weather conditions because thousands of crores are on the line if you don't launch it at the right time. So the solution, all these solutions have a nearly 100% accuracy. But is it an adequate metric? Can we really depend on accuracy as a solution for most of the ML products? And the answer is a big no. So here I just try to solidify my opinion on why we don't need accuracy. And let's dive deep into some of the technical details. So whenever we use any data set from Kaggle or any predefined data set, it's a highly imbalanced data set. So imbalance basically means that if you have two classes, terrorists and non-terrorists, there would be 900,983 people who are not terrorists and 17 people are terrorists. So how do we depend on a model to just take these 17 people, take their features, and then test on someone else whether they are terrorists or not. And similarly, even if you have around 200 people labeled as lone defaulters, and the other 100,000 not as lone defaulters, how the heck are you going to predict whether they default on the loan or not in the production environment? So this is a really bad model. And let's see the solutions. Solution, as I've been discussing, is basically precision and recall. Now, what the heck is precision and recall? So now, finally, I'm going to come into why we use all this and some of the formulae, and I'll also tell you on which situations we can use these formulae. And so precision basically measures out of all the positively predicted examples. So let's take any example would have a positive and a negative label. So out of all those, how many detections by a model were correct? So how many detections are there where y is correct and y cap is also the same? And recall measures out of all the actually positive examples that are in your data set and that are predicted by the model. How many were how many were able to be identified by a model? This model can be anything from logistic regression, SVMs, and naive Bayes as well. So now you don't need to measure. You don't need to memorize the terms precision and recall. So usually people just go ahead and memorize them. But let me make things very, very simple for you. So, let's just absorb the content and let's not memorize it. If we memorize it, we'll forget about it tomorrow. I'm pretty sure about that. Okay, so confusion matrix is the whole magic key or magic portion that's going to help us to learn precision and recall. So like I mentioned, if you have the actual values as positive, predicted values as positive, they are two positive examples. And if the actual values are positive, but we predict them as negative, and then they are false positive values. And similarly, if the actual values are positive and we predict them as negative, they are false negative. And similarly, you can also calculate the true negative rate. So what are the observations from this predicted example? So let's look up under the predicted heading and the positive row. So the predicted heading is here and the positive row is here. So it comprises of true positive and false positive values. So denominator basically quantifies what precision is. So precision basically is the denominator of the precision is true positive plus false positive values. So these include values that are predicted correctly by a model and also that are not predicted correctly by a model. Like the label marks it as negative, but your model predicts it as a positive. So all these are all the positive values. They can be either wrong or right. Okay, since we are interested in finding only the true positive values for both the precision and recall. So the precision would be all the true positive values where the label in our data set is true and the model also predicts true, divided by all the positive values. So this can be the ones which are really true and the ones which are false also. So either of them. And recall is the same thing, but here what we're doing is we basically in the denominator, we are going to use the two positive values, the ones which are really positive, and the false negative, the ones which have been predicted as negative by your particular model, but in the data set, it's labeled as positive. Alright, so what are the main deductions from this equation? So when one quantity precision increases, so when one quantity the precision increases, the recall decreases and vice versa. So when the recall decreases, the precision increases. So they have a trade-off, and we'll decide how to tackle this trade-off in a very slick or very smart manner. But the first thing is, how do we prioritize? Should we use precision or should we use recall, and the vice versa case as well. So there's a secret key, and the secret key is we can't afford to have any false negatives. So let's say we are a hospital and we want to predict whether a person has cancer or not. So it's better if they give them cancer treatment even if they don't have cancer, instead of just telling them they don't have cancer and send them home. So here's what is explained. So in this case, we always prioritize recall over precision because recall gives a very, very high penalty if you have a lot of false negative values. And when similarly, when we can't afford to have any false positive values, so at that time we can prioritize recall. We can prioritize precision over recall. So let's say we have an object detection algorithm and we don't want any kind of incorrect detections. Then precision is important over recall. So yesterday we had gone to the tech summit and there was this a company which manages all these security cameras and they apply ML algorithms to detect whether there's a theft or not. So those people would surely prioritize precision over recall because you don't want to catch someone who is a thief, but he's actually a person residing in the apartment. And even intrusion detection systems like Amazon Ring is also a very good example of where you would prioritize precision over recall. So there's a really interesting video on YouTube if anyone's interested to learn about how Amazon Ring really works and the performance metrics behind it. Okay, so I have a question for you guys. If the cost of false positives is more than the false of cost negatives, then what metric should be used? I actually told the answer a few slides back. Not sure. Okay. So I'll tell you guys later. So typical scenarios in a precision recall problem. So we basically have 4 scenarios. One is higher recall, but you have lesser precision. So what do we do in this case? So let's assume that we don't have something called as F1 score. I know people know about F1 score, and it's basically combines both precision and recall. But let's say we don't have that in this context. And in the context, I'm going to take an example of an object detection model. So let's say we have a single model which detects only one class, and it detects only the classes which are there on the ground. So let's say human and non-human objects. So let's say most of the ground objects are false positives. So in that case, what we would do is we would the recall would be high, but the precision would be less. So this is one example of that. But where do we have higher precision and less recall? Like as you may have guessed, most of the ground objects that are detected with accuracy, but some of them are not detected. So they're still some kind of object, but they are detected as not objects by our object detection algorithm. So in this case, we have all false negatives. And similarly, we have this special case, 2 special cases where you have higher precision and higher recall. So ideal scenario is where your model has a very good training accuracy, and it has detected the ground objects with 100% accuracy. So every object which is on the ground has been detected. But in this case, the model very likely overfits. So you should never have a model with higher precision and higher recall. It's not possible because when one increases, the other decreases. And similarly, there can't be any model with low precision and low recall as well. So this is a very worst case, and it's really there's a problem in the data set if you get this kind of outputs from your performance metrics. In this case, we have a higher variance scenario, like it underfits a lot, and where the ground objects are not detected as well. So the objects which are there in our training data set, even those are not detected well by our model, and the detected objects which have been actually detected by the model, they are also not ground objects. So let's say an airplane is detected as a ground object by the model. So in this case, we have a lot of false positives. Okay, so I discussed this question as well. Anyone? I have a reward for you, and I'm not bluffing. What metric is used in cancer detection? Recall. Recall is more important. I'll give you the reward. It's okay to classify a healthy person, like I mentioned, as having cancer. So if I go to a hospital and I have a chest pain, and I say the doctor, he says that you might or may not have cancer, but the doctor can't send you home without giving you any treatment, because if you have cancer, you lose his license. So what we basically do is give him some kind of treatment so that his condition improves. And here it's basically okay to treat false negative patients and give them treatment because a person's life is at stake. Okay, so what is the key metric in Netflix recommendations? So we use Netflix every day, right? Anyone?
Precision.
Based on the recent.
Yeah, your precision on your recall. Sorry? No, tell. It's fine if you know.
So let's say you watched Friends right now.
Yeah.
You will get recommended a show like Office or something.
So is it, do you use precision or do you use recall here?
Precision.
So we use recall, I think. So it's recall according to the job.
So precision is more important here, okay, because I'll tell you why. So you let's say you're an action fan and you know the model misses out to recommend you Top Gun Maverick to some action freak users like me. But you should not be recommended anything like romantic movies that are false positives that really don't affect me, right? So even if I don't recommend Top Gun Maverick and I recommend some other a mix of action and romantic strip, but we surely shouldn't recommend any irrelevant romantic movies. So in this case, vision is very important. Again, NSF2 is not safe for work images. So
Recall.
what would be easier to detect not safe for work images? Take a guess, it's either one of the two.
Recall.
Decision.
Recall.
Recall is more important. It's okay to, so it's a really simple logic. So if we end up classifying, some good image or some decent image as an NSFW image, it's fine, but it's very risky to predict whether as an NSFW image. So if we predict it as a non-work sensitive image, then it's a huge problem for the organization. Right? If we have some, let's say, a good image or safe for work image, then we can change the label later and train it again. But if you do it the other way, it's certainly wrong. Now, I have an Amazon question for you guys. So let's say you're going to write an algorithm for deduplication. So if you have duplicate records, you have to remove it, and that's your task. And there are a few conditions. So it does not access the exact equality. So if you have two records with the same features, it certainly detects that it has duplicate images, duplicate records. But here I'm saying that if a couple of features have some changes, still I'll be classifying them as duplicate records. So I wanted to assess the problem. So the problem is very simple and come up with a good performance metric. So 4 questions I have. Anyway, what's a positive class? It's either one of the two. It's either detects a duplicate or doesn't. So what's going to be your main focus?
Duplicates. Identify duplicates.
Identify duplicates, right? Okay. So yeah, the positive class is that the record is a duplicate. So this is our sole focus, and we can take the non-duplicate records. This is a typo. So the non-duplicate records are the negative classes. But also preferably what is done in the industry is that you can use the non-duplicate records, which are certainly the minority class, and you can also take it as a positive class. But here, just for simplicity, I've taken the positive classes, that is duplicate records, as the labels that I want to predict. So now coming back, what does 85% recall mean? So this is the question which has been asked. And 85% recall basically means that 85% of duplicate records are detected, but the remaining 15% are not detected by the algorithm. And similarly, 75% precision means that the 75% of the flagged records that are actually duplicates, while the remaining are not duplicates. So this is how it predicts with 75% precision. But here, even though we have the problem with the low precision is that even though we have a lot of irrelevant records to filter through, there might be a lot of records that may not necessarily be duplicates. Okay, so which is a better metric? Here, I've given a couple of examples. So here, obviously recall is a better metric. And to determine the idea of how to manage the precision recall trade-off in this example, consider how much it costs for a person to review the records, and what are the impacts of keeping a duplicate record in the database. So if you have duplicate records, then it's certainly going to increase your memory. And if you don't have an ML model and still you need someone to review the records, then also it's going to increase the manpower. So an ML model with a better recall is way better than an ML model with a higher precision. So F1 score. So F1 score is really simple. It's the weighted harmonic mean of the precision and the recall. So we use two metrics, precision and recall. And F1 score gives us a combined estimate of both. So it doesn't matter whether the precision is high or the recall is low and vice versa. It still gives us a very good estimate. And why do we use exact harmonic mean and not geometric or the normal mean? In an ideal scenario, we would want both our precision and recall to be 1. But from the previous slides, you know that either one increases, the other decreases. So they can't be a case where both of them are 1 or both of them are 0.8 and so on. So let's say there's a model with a precision of 0.9 and a recall of 0.4. So the arithmetic mean over here is 0.65, geometric mean is 0.6, and harmonic mean is 0.55. So as you have noticed, the harmonic mean is kind of middle value between the arithmetic mean and geometric mean. Not exactly, but kind of the middle value. So essentially, we see that the harmonic mean penalizes the model when one of either precision or recall is low. So if one is very low, the other one is very high. So harmonic mean penalizes it, and that can't be used as a metric for us. Okay, so now let's jump on to the code examples.